starting with just some kind of algebra and trig. So we're going to just look at basic expressions to begin with. And when we look at this, let's just do a distributive property and multiply it out. That looks like a distributive property, doesn't it? So just go, write it down, just say cotangent x times sine x, then multiply like this, so that's going to be minus cotangent x times secant x. Okay, now we've already learned the fundamental identities, and the faster you get them memorized, the better it is for you. Okay, now what we're going to do is what you have to learn to do on these problems basically is just sort of try something. Okay, is there an identity for the cotangent that we learned? Cosine over sine. Okay, so we could do that maybe. Is there an identity for the secant? Yes. 1 over cosine. Okay, so what I'm going to do on this is we're going to replace these. So this thing right here is going to replace with cosine x over sine x. And like I say, guys, you have to learn to just try stuff on this. Okay, you're not always going to do it the right way, but you try. Now I'm going to leave the sine x alone. How come? It's going to cancel out anyway. Okay, we're trying to simplify this. And then the cotangent is the cosine x over sine x. And then what do you replace the secant with? That was 1 over cosine, right? So those are all identities that you got to know. Now if you go through and do that, of course the sines divide out, the cosines divide out. So it looks like what you're going to be left with then is a cosine x here, like that. And then you have 1 over sine left here, like that. Right, so after you cancel that out, then what could you do with 1 over sine? That's the cosecant. Yeah, we have an identity that says the cosecant is equal to 1 over sine x. Okay, so what you do now is your final simplified answer could be written like this. Okay, what you're trying to do is you're trying to use identities to simplify that expression as much as you can. Okay, and as we're doing this, you can kind of look at the identity sheet. All the identities that I used on this are on this sheet. The ratio identities, I used that. The reciprocal identities, I used that. Okay, so they're all there. Okay, all right, does that make sense, what I did? Okay, what do you think you would do on the problem number 2? Looks like a FOIL problem, doesn't it? So that's exactly what we're going to do. Okay, so we just have trig functions in there. So you're going to start by doing the first term. So 1 times 1 is going to give 1. Then the outside term is 1 times cosine. So that's going to be plus cosine x. The inside term is going to be negative cosine x. And what's the last term going to be? Yeah, negative cosine squared x, like that. Okay? So what do you see happening? We have a cancellation, and then we have this. Okay, so that's the result of the foiling, but there is more we could potentially do on this problem. Okay, when you see cosine squared pop up in a problem, what you want to think about immediately is this identity right here. Okay, that's one of the identities we learned. Okay, so what we want to try to do is simplify this further if we can, just see what happens. So there's a couple of ways to do this. One way to do this is to move this cosine to this side of the equation. I mean, an identity is an equation. And you got to keep in mind, there's more than one way to do this. I just see something, and with experience, you're going to learn to see some of the same things that I see. Okay, so why did I move cosine x squared x over to that side anyway? Because that shows that it's equal to the sine, right? So you're going to do a substitution. On this section, you're just going to substitute equals for equals. So that thing right there is really equal to what? The sine squared x, okay? And again, you got to be brave on these problems. You just got to try stuff. There's more than one way to do that. You also could have moved the sine to the other side and did a substitution, and you would have got the same answer, okay? So what you're trying to learn how to do is use identities to simplify trigonometric expressions. So that's how that goes. Okay, does that look fairly good for starters? Okay, all right. So we're going to go through some other things here on this and kind of work with simplification. This type of a problem right here, what do you think you'd do first? That looks like a distributive property, right? So you're going to take this thing and multiply it by that thing and then by that thing. So yeah, it's a distributive property. So just write down what you have. Then we'll worry about identities next. So we have cosine theta, sine theta, secant theta, minus, and then we're going to have cosine theta, sine theta, cosecant theta. Now there's several ways to look at this. Just kind of depends on what you see in the problem. So let's look at some things that we might be able to use identities for. Do you have an identity for a secant?
Yes.
Yeah, that's 1 over cosine. Do you have an identity for a cosecant? Okay, and you don't have to do this problem exactly the way I'm going to do it. I'm just going to do the way I think students might see it, the most easy. So that's cosine, that's sine. We're going to replace the secant with 1 over cosine, then what's going to happen? Okay, right? Over here, we're going to leave the cosine theta and sine theta alone. You're going to replace the cosecant with 1 over sine. What happens? Okay, like that, right? Okay, so what we're left with is sine theta minus cosine theta. And you're not going to go any further than that. You don't have anything else that you could do. If you did anything else on that, you'd be making it more complicated. Okay, do you see what I did? Now I want to ask you guys a question on this. This is also really important to learn to look for. Do you know what sine times cosecant is? Like that? 1. Okay, so you could have done that also. Okay, that's another form of the identity. So if you see a sine times a cosecant, that's 1. A cosine times a secant is 1. So it just kind of depends on what you see in the problem. Okay? All right, now we're going to get into something a little bit different with these. Instead of using identities at the beginning on this, what we're trying to do is simplify, and we're going to try to look at some of our factoring. So usually when I teach problems like this, I like to first of all see if you remember your algebra. So write this down first of all, okay? Then we'll do the trig problem here in just a minute. Write that down. Okay, so if you were in like a Math 55 class at CCD or college algebra, how would you simplify something like that? You'd factor and then cancel, right? Okay, so this depends on what your factoring skill is. Do you guys know how to factor x squared minus 1?
Yes.
That's the difference of 2 squares, right? So that's the one that goes x and x, 1 and 1, plus and minus. Okay, if you need to review your factoring, then you need to do that. So that would cross out and you'd have an answer of x minus 1, right? Okay, so when we do this trig problem, we're going to do this exactly the same way. We're just going to leave the trig functions in the way they are. So if you're factoring sine squared x minus 1, you're going to put sine x and sine x. You're going to put 1 and 1. And you're going to put a plus and a minus like that. Okay? Sine x plus 1 stays alone. So what's the answer to this problem?
X minus 1.
There you go. Okay, that cancels out. So yeah, you would end up with sine x minus 1 would be your answer to your problem. So we're going to kind of now focus on some factoring issues on these problems. Okay, so that look okay? Okay. All right. Now, if you had a problem like this in college algebra, say that you had this problem, x squared plus x squared times y squared, and I wanted you to factor this, how would you factor that? You would take a common factor out, right? So in this case, you have something that's the same, so you take it out, and you would say x squared times 1 gives that first term, and x squared times y squared gives that term. So this problem's done the same way. It's got a common factor. The common factor on this is the sine. So you're going to go ahead and take sine squared x out, and then we'll see what happens from that stage. Okay? All right, so let's go ahead and do that. Take the sine squared out, put a parenthesis. Now what goes in the parenthesis? What goes there? 1. And what goes here? Good. Cotangent squared x like that. Every time you factor something, multiply it out in your head and make sure it's right. Okay? So there's a tendency on this to think, well, maybe I'm done. Look at your identity sheet. On your identity, you'll find something on here that says 1 plus cotangent. Okay? The quicker you get it memorized, the quicker you can do this, but you can refer to this stuff while you're doing homework and stuff So you have 1 plus cotangent squared alpha equals cosecant squared alpha is what's on my identity sheet. So what you're going to end up doing on this, again, is you replace equals for equals. This thing is equal to this thing, right? So what you do is you substitute equals for equals. So you're going to get sine squared x times cosecant squared x. Do you know what the answer is? Just like that?
1.
It's 1, okay? If you don't know it's 1, then you might do it this way. You might say, well, the cosecant, isn't that 1 over, I don't know why it does that, 1 over sine, then they would cancel out, so that would leave you 1, wouldn't it? But you don't have to show that last step, because to me, if you see that sine squared times cosecant squared is 1, just write it down. That's good. That's what I want you to see. Okay? All right. The factoring, does that look okay? Okay. All right. Okay, so if we go to this next thing here, let's again look at algebra on this. Okay, let's say that you're in college algebra and you have this problem, and I ask you to factor it. Would you be able to factor that? You guys remember what you call that kind of factoring problem? It's a difference of two squares. Okay, anytime you have an even exponent, it's a perfect square, because what number multiplied by itself gives you x to the fourth?
2.
X squared and x squared, right? What number times itself gives you y to the fourth? X squared does, or y squared does. Then you have a plus or minus, right? Okay. Now, how about this one? Does this one factor any further? That's another difference of two squares, right? So this one is going to go like this. You're going to say x and x, y and y, plus and minus. This one does not factor any further. The reason is because it's a sum. You can only factor differences of two squares. You can't factor sums. Does that look familiar? This is the kind of stuff when you're working in this chapter that you're going to have to review, because you're going to do a lot of factoring over the next couple of chapters. And that a lot of times is an area that students are a little weak in. So when we do this problem, we see that it's a difference of two squares. So you want to write this just like I did that. You're going to say tangent squared x times tangent squared x, like that. You're going to say secant squared x times secant squared x, like that. Now we're going to start that way, and then we're going to have a plus or minus. Now, you could go further, like I did there. But remember, you're learning about identities now. So if you look at your identity sheet, is there an identity that has a secant squared and a tangent squared in it? Look at your Pythagorean identities. It's there. So I'm going to write it down. So that identity is always written like this. It's always written as 1 plus tangent squared x, I'm going to use the same variables we have, equals secant squared x. So it's logical in this problem, if we're going to simplify it, to work with that identity instead of factoring this further. Okay, so what I'm going to do on this, and you've got several ways you can do this. It's really up to you. Now this is just the way I'm going to choose to do this. This is just my personal choice. When I see a secant, what is a secant? It's that. So let's just plug it in and substitute, and let's see what happens. Okay? Now this is one way to do this. Like I say, there's more than one ways to do this. This is just what I see. So this is I'm going to leave that tangent alone. I'm going to replace the one I highlighted with what it's equal to, tangent squared x. Okay, so I just do a substitution. Now you've got to be real careful on the next one. Now I'm going to put a bracket there. That's probably the best way to do this. Now, what am I going to plug in for that secant squared? What it's equal to.
-1.
Okay, so we got that. So I'm taking that secant squared and I'm replacing it with what it's equal to in that identity. Do you see why I did parentheses there? Because if you don't, you're going to miss it, because you got to distribute that negative through there. All right, now in the left parenthesis, those are like terms, right? So a tangent plus a tangent is 2 tangent. So that would be 2 tangent squared x plus 1. Now when you do this thing, you're going to have tangent squared x minus 1 minus tangent squared x. So what happens to the tangents? They cancel, right? So now we could write the answer like this. This is just a -1 left over. And then write down the first parenthesis, and then you could multiply that out, and then you would have a good simplified answer. Okay, so just multiply that. You're going to have -2 tangent squared x minus 1 like that. Okay? Got any questions about that? Here's the attendance. I need you to pass that around. Okay? All right, you guys follow what I did? Kind of quiet. They're getting a little harder. They're going to get a little harder as we go through these today. But it's mainly, what are you doing? Substituting equals for equals. Okay, and the thing that we're going to get into in this section is I can teach you principles to help you understand how to do this, but I can't teach you a direct procedure. Okay, especially when we start doing the proofs that we're going to start doing here in a few minutes. Okay, so you have to be creative. You have to be bold and try something sometimes. Okay, all right, how do you think you'd work out number 7 to start with? Probably FOIL it, exactly. So let's do that, okay? It's something squared. So let's go ahead and write it out twice. And then we can multiply it out by FOIL. And I'll also, on this problem, after I FOIL it, I'll show you how you could do this step in your head anyway, if you don't already how to do that. Okay, so we're going to write it out twice. And you want to go ahead and just start doing the FOIL. So the first term is cosine squared x. The outside term is going to be minus cosine x sine x. You can write that in any order. The inside term is going to be minus sine x cosine x. And then the last term is going to be positive sine squared x, like that. Okay. Now, do you see those like terms? Those are exactly alike. They're in a backwards order, but that doesn't matter if you multiply, so you have 2 of those. So you would have cosine squared x minus 2 cosine x sine x plus sine squared x like that. So what I've done is multiplied that out. Does that look okay? Yeah. That's FOIL. Okay. Now, before I finish this, there is more we can do. You can kind of think about the other thing you can do on here. Let me show you how you could do this in your head. I think the higher up you get in math, particularly if you're going to take calculus, you want to know how to square something like this in your head. The way you square this in your head is you do this. You square the first term. You square the last term. Now, if you're squaring a negative number, that's going to give you a positive number, right? Okay. Now, you multiply these two things together, which is a positive times a negative. That's a negative sine x cosine x. Then you double it, okay? Because what happens if you square a binomial, the inner and outer will always be the same, so they get doubled. So you could get the answer in your head like that. That's a good thing to learn to practice, okay? What else could I do to this problem to finish it up? I'm hoping you see something. Yeah, this right here. Isn't this an identity right there? So the cosine squared plus the sine squared is what? It's 1. So you just plug it in, you get 1. So then what you would have for a final answer is you would just say 1 minus 2 cosine x sine x. Now, it doesn't matter what order you put the cosine or sine in. That's up to you. Okay, like that. Okay, does that look pretty good? Okay. Okay, now we're going to focus a little bit on factoring, just a little bit more here, and then we'll kind of finish up with starting to get into the proofs here. Okay, this is a kind of problem that I see students do not have as strong a background for as I would like typically. So this problem looks a lot like this problem. I'm just pretending like the cosine's not there and just x's are there. So let's look at the algebra problem. If you were going to factor 8x squared plus 16x plus 8, what would you do first? Take an 8 out. Good. That's exactly what I wanted to hear. You always go for common factors. So 8 times x squared is 8x squared. 8 times 2 is 16. 8 times 1 is going to be 8. You start there. Now you can go further, can't you? Yes. Because you have a trinomial. So if you have a trinomial, you want to go a little bit further and just draw your two parentheses out and do that. So go ahead and do that. So we would have 8. You would draw your two parentheses. Now you're looking inside the parentheses. Don't pay any attention to the 8. So you would have x and x. The number that would multiply to give 1 would be 1 and 1. And then the inner term and the outer term got to add up to 2. So how do you make the signs go? Plus, plus. Okay, like that. So you could write it like that, or you could even write it as 8 times x plus 1 to the second, because it's the same factor twice. Okay? So this problem is done the same way. A lot of times students, when they take trigonometry, have a little bit of a struggle for a little while going from that point, the algebra point, to the trig point. It's the same thought process. So what we're going to do on this one is we're going to take the 8 out. So you want to go ahead and start that way. So that's going to give cosine squared x plus 2 cosine x plus 1, like that. So it's the same principle. You make a step in your mind, multiply the 8 through that and make sure it's right. Then bring down the 8. Now draw two parentheses, like this. And what you're going to be looking at is the cosine squared. So you're going to use cosine x times cosine x to get that. You're going to use 1 times 1. Okay. And if you look at the way the FOIL works, that inner term is 1 cosine. This outer term is 1 cosine. What are you trying to do? You're trying to make it add up to 2 cosine. So the signs are both going to be positive, right? Yeah. That's it. And that's a good answer. You can leave the answer like that if you want to. Or you could write it as 8 times cosine x plus 1 to the second. Now the directions of this problem are to factor, so you want to leave that in a factored form. That's what we did. Okay, you don't multiply it out. You're done. You factored. Okay, and there isn't any simplifying you can do on that problem. We don't have an identity for cosine x plus 1. Okay. Okay. So let's do a little bit more with this. Let's go ahead and factor this. Let's do this problem first. So if you're doing a problem like this, this is a trinomial, so it's the same principle. It's exactly the same principle. So the first term is 1, so what are you going to use? 1 and 1. The last term is x to the 4th, so what are you going to use? Probably x squared and x squared, okay? This problem has a certain structure to it, so it would go like that. Now you figure out your signs to get that middle term. So that is a 1x squared. This is another 1x squared. I think I left something off on this. I think I intended for this to be a 2. Okay, so why don't you squeeze that 2 in there? Right? Otherwise, I'm not showing you what I want to show you. Okay, so how do you make this add up to a negative 2x to the second? Yeah, 2 minus signs like that. Okay, all right. So you'd have that, okay, and that checks out. But the other thing I want you to look for, because you got to learn to look for this stuff in this class, is do these two things factor any further? Yeah. Yes. Yeah, those are differences of 2 squares again, aren't they? Okay, so good. So what you want to do is you want to go like this. Okay, you just say, for this first one, you say 1 and 1, x and x, plus and minus. Okay, that's how that factors. And then the second one is exactly the same thing. So you just say 1 plus x, 1 minus x, like that. Okay, and that's okay to leave the answer in that factored form like that. But you could also say, well, we have 2 of these, so we could say 1 plus x to the second, and we have 2 of these, so you could say 1 minus x to the second, like that. So that's the factoring that we're going to do on the trig problem. Does that look okay? Okay. So you'll kind of find out when you start working with your homework if your factoring skills are up to par. If they're not, you got to work on it. So we're going to start this one same way. Okay, first term's 1, so we use 1 and 1. What are you going to use for the last term? Sine squared x. Sine squared x. Sine squared x. Okay, now I'm going to go ahead and factor this because that's the problem on here, what we're supposed to be doing. And then it's got to be 2 minus signs because you're trying to make the inner and the outer add up to negative 2 sine squared x. Okay, now the directions really are just factor. So we're going to go ahead and factor this. So we're going to do the difference of 2 squares. So we're going to factor this, this first parenthesis. like that, and then that's the difference of two squares, so you go like this. You go 1 and 1, sine x, and you go plus and minus, like that, so that factors that. Then over here you do basically the same thing. You're going to go 1 and 1, sine x, plus and minus, like that. Okay? There is something else we could have done on this problem with an identity, but I'm just going to factor it. Okay? That's my choice. Okay? Not too as concerned about using identities on this problem as I am factoring. So now what you would do is, since we have two of those, we could write that as 1 plus sine x squared. We have two of these, so we write that as 1 minus sine x squared, like that. That's as far as I want to take that. Okay? There's other approaches. You do have an identity for 1 minus sine squared x. Okay? Now I'm going to show that on there because I want to kind of have you look at this to kind of prepare us for other things we're doing. So that's the factored answer right there. That's as far as you can factor that. Okay? But I do, before we go to the next problem, want to show you one other thing. Okay? Let's go back to this point where we have 1 minus sine squared x times 1 minus sine squared x. Okay, is there an identity that has a sine squared in it? Yeah, okay, let's work with that a little bit. So if you look at the identity, sine squared x plus cosine squared x equals 1, 1 minus sine x is in this identity, right? You could move the sine to this side, right? So you would get the cosine squared x equals 1 minus sine squared x. When you got identities, they are equations. They can be rearranged, okay? So let's look at it this way then. So what could you replace 1 minus sine squared x with then? Cosine. So you could do it this way. Okay, your answer will look kind of weird, but it's a valid way to do this. If you wanted to simplify it, this would be the way to do it. So that just becomes cosine squared x times cosine squared x. What is that? Cosine to the fourth x, because you're adding exponents, right? Okay, just dig in your algebra background. If you have x squared times x squared, that's x to the fourth, right? Okay, so you can do it that way. That is a valid answer. That's a simplified answer. It's a totally different approach to the problem, but it's also correct. Okay, so how's the factoring look? Okay, all right, you guys seem okay. Okay, I'm always concerned on factoring because I sure do see a lot of issues with that in this class. Okay, on this problem 10, this is the factoring problem that students are the worst at typically. I shouldn't say worse, I should say that they need to review the most. That's a more positive thing for a teacher to say, right? Okay, so this is sort of a trial and error trinomial. Whenever you have a trinomial and you have a number in front that's not 1, the factoring's a little bit more difficult. That's your last term, and then this is a combination of the outer and inner. So you have to do this by trial and error. Now, a lot of you maybe had a teacher that taught you how to make it into a factor by grouping problem. It's okay, but it's not a good habit for higher math. So when I teach like Math 55, I don't usually teach them any other way other than trial and error, because that's the best approach for higher math, okay? So what we're going to do on this is draw two parentheses, and there's actually several possibilities. For the first term, what are your choices? You could either go 2x and 2x, or what else? 4x and 1x, okay? For the 63, you got lots of possibilities. You got 1 and 63, you got 3 and 21, you got 7 and 9, okay? You just kind of write them down if you have to. Now, what you have to do is you have to just sort of work with it and try things. So I'm going to try close together. I always tell students most of the time, just try close together. I'll see what happens. It may or may not work. And the other thing I want to say is you cannot do this problem in your head. I see that from students all the time. They think they can do it in your head. You can't do it in your head. You got to write something on your paper. So you just write down 2x and 2x. Then you write down 7 and 9. And then you see if it'll work. It may not work. So if you look at this, you're going to have 14x there,
18,
18x there. What are you shooting for?
29,
I guess that's a y. I think that right there is supposed to be an x, is what I meant for that to be. Okay? All right, that doesn't work. So it doesn't work. Okay? So you could try something else. You could try like 3 and 21. You could try 1 and 63. I'm pretty confident they don't work. So let's try this approach. Okay? Now I got an eraser on this thing, which is just so cool. So I can go erase. Let's take away that. And then let's redo this. How about let's try 4 and 1. And with a little practice, you can start kind of at least visualizing these in your head a little bit better there. So if we did 4 and 1, let's maybe try, let's see, let's try like this. And I may have it backwards, so let's try it. I think I do have that backwards. That's 28 and 9, so let's go like this. I was trying to kind of reason that in my head. And I'm just sort of a person that needs to see something visually. So let's put a 4x there, and let's put an x there. Now that comes together to make a 7x. This becomes a 36x. I think that works, doesn't it? Mm-hmm. Okay. So what has to be positive, the 7 or the 36? Okay, you got to go positive 7 minus 36. So that means you're going to have a plus with the 7 and a minus like that. Okay, now that's trial and error. Now you're going to deal with that from time to time in this class. So what that means is when we factor this thing over here, we're going to do the same approach. And see, when you're doing these problems, you can always look at the algebra problem if that helps you. So what we're going to do is we're going to go 4 tangent y and tangent y, just like over here we did 4 and 1. Then we're going to go 7 and 9. Plus and minus, and then that works out. And then notice on here the inside term is 7 tangent y, and it's a positive. The outer term here is negative 36 tangent y. So that's going to give what we're after like that. So it's all checkable too. And a lot of times students are doing problems, and I can tell they never check their factoring, and I don't understand why. Because if you don't check your factoring and you're doing a longer problem, you're wasting your time. Okay, do it. Check it. You factor something, verify it's right. That's one of the things you got to learn in math as you kind of proceed through the study. Check stuff. Okay. All right. Now here's my favorite stuff. This is really fun too. I promise you. We're going to prove identities. Okay. We're going to prove that one side is the same as the other side. Okay. Now, before I do anything on this, I think I had thought that I had put on here a basic example of an identity on here. I was going to see if I did put that on there. I don't remember if I did or not. Okay, that's crap out. I don't know if I put it on your notes or something else. Yeah, go to that 15 and see if I put that on there. I don't know if I did. If I didn't, it doesn't matter. But, did I? Okay. All right. The reason I want to start with this is students a lot of times when they're learning how to do a proof, and it's just because you're a beginner at it typically, is don't write their steps very good. It's like chaos everywhere, here and there and everywhere. This is how I want you to do a proof. Okay, and we'll kind of run through this in a minute. But what you always want to do is you want to pick a side. You're trying to prove that these two sides of this equation are equal. That's what you're really doing. So typically what you do is you write down the side that you think is the most complex. It's the one that has the most stuff on it. So clearly the left side is more difficult than the right side. So you write it down. And you just keep substituting equals for equals, and eventually your goal is to hit the other side. Now, I'm not going to go through the details of this yet, but all I'm trying to say right now is when you do a proof, your proofs need to look like that and nothing else. Okay, nothing else is acceptable. You write a side, equal signs until you hit the other side. Okay, no stuff all over the paper, sideways, upside down. No messes. It's got to be clean like this, okay? Trying to get you to think mathematically and think in a certain kind of system. Okay, now we're going to go back up to where I was, and let's do this, this first proof here, okay? So again, what you want to do, you want to start by writing it down like this. Just write down proof. And what you want to do is pick a side. Now, you're not always going to know at the beginning which side's the best one, okay? So you just try a side. Now, what I'm going to have you do on this is let's just write down the left side. Just write it down. Do not start your proofs any other way. Pick a side and write it down, and then write an equal sign, seriously. That's always how you must start these things, okay? You got to learn to do this stuff right. Now, you got to know identities, and you just got to try stuff, okay? Do we have an identity for tangent? It's sine over cosine. Let's try and see where it leads us. Do we have one for cotangent? Cosine over sine. Remember, you try and you see where it leads us. There is no procedure I can teach you on this that's always just going to simply get you to a correct proof. You have to try things. So let's go ahead and do that substitution, and let's see where it leads us. It may lead us someplace. It may not lead us anywhere. If it doesn't lead us anywhere, we just throw our paper away and we try again. Okay, seriously, that's what you do. Now, general rule of thumb. If you have two fractions that need to be added, add them. Okay, look at the right side. The right side doesn't have any fractions at all. It just has one thing. Clearly, these things have been collected. What's the common denominator on this? Yeah, sine cosine. So that means you got to multiply this one by sine x over sine x. You got to multiply this one by cosine x over cosine x like that. Okay, that's clearly the way you got to start that. Now, let's go ahead and write what we have. Okay, this, when you multiply it out, is going to be sine squared x. And it doesn't matter what order you write the denominator in, but I'm going to go ahead and, well, no, actually, let's leave it the way it is now that I think of it. It doesn't matter. You would see this at the end of the problem anyway. So just go ahead and multiply it out. So you're going to have cosine x, sine x. And over here, you're going to have cosine squared x. And then I'm going to write this as cosine x, sine x. Let's just make them the same. Okay, now what do? You collect them, you add the fractions, so you combine the numerator, and you keep the denominator. Okay, so we are doing some basic algebra on that too. Okay, what do you see? Sine squared plus cosine squared is 1, isn't it? Okay, so this now needs to be written as 1 over cosine x sine x. Now, throughout your proof, you always want to look at your goal. Your goal is this right here. So my question to you is, do you see the secant and cosecant embedded in this expression? Yeah, okay, now you can just write the answer, but technically you're really looking at 1 over cosine x times 1 over sine x. You can break it up like that. Okay, what is 1 over cosine? That's the secant. And what is 1 over sine? Cosecant. We are done. We have proved it. Okay? Like that. Isn't that cool? Okay, so that means that that is an identity. That tangent plus cotangent equals secant x times cosecant x is an identity. And look at the elegance of the proof. I wrote a side. I just kept substituting equals for equals until I hit my goal. And that's what you got to try to do. Okay, just don't lose those equal signs. Keep going like that. Okay, so let's see what we got on this next one here. Okay, the first thing you always want to consider on these problems is which side do you think is more complicated? So what do you think, left or right side? Probably the right side. It has two trig functions in it, so let's go ahead and write that down. 2 cosine squared theta plus sine squared theta, like that. And we're going to see where it leads us, okay? Now, look at your goal. Your goal only has a cosine in it, right? We have a sine. We'd like to make that sine go away. So the identity that's probably useful on this is sine squared theta plus cosine squared theta equals 1. Now, if you need to do any scratch work at the side of your proof, do it at the side. Don't put it in your proof. Okay, what we're going to do on this is basically this idea. We would like to replace that sign with what it's equal to in this identity. So one of the things you got to learn to do on this is rearrange things. So the sine squared theta equals 1 minus cosine squared theta. This is scratch work over here. Don't put that as a part of your proof. I don't want to see it. Okay? All right. And you don't even have to have scratch work on your presentation. So the idea is that sine is going to get replaced with that. Okay? So now we're going to go back to our proof, and we're going to leave the cosine squared alone, and then the sine squared is going to get replaced with this. Okay? See what I'm doing? Okay, now what? These are like terms, aren't they? 2 cosine squared minus 1 cosine squared is cosine squared theta plus 1. Wow, we already proved it. It's already done. Sometimes proofs take 2 steps. Sometimes they take 1,000,000. Well, maybe not 1,000,000. Okay? There is a mathematician who proved Fermat's last theorem, and it was a whole book. That was an unsolved math problem for several centuries, and he did that last decade. Whole book. Okay, so let's move on. Let's do a few of the ones that are a little harder. Now, on these kind of problems right here, first of all, this problem, which side is more complicated? Clearly. Okay, so write it down. Okay, so you always start by picking a side, writing it down, and then putting an equal sign. Do not start your proof any other way. Okay? And again, sometimes you end up making a proof more complicated before you make it more simple. Or I should say, you make an expression more complicated before you end up simplifying it. So a rule of thumb that often helps a lot of times is, if you can, try to make everything just have sines and cosines. Okay, so that's what I'm going to kind of look at on this problem is, we have an identity for a tangent, we have one for a cotangent, and we have one for a cosecant. So that's how I'm going to choose to start. You just, and remember, you try stuff. Okay, so what is the tangent equal to? What's an identity? It's sine over cosine. Yeah, we're making this a little more complicated looking, but that's okay. Eventually it's going to simplify out. And then the bottom, what's the cotangent? That's cosine over sine. Okay, and the cosecant is 1 over sine. Okay? Now, this is what you call a complex fraction. If you have complex fractions, you want to make them go away. Okay? And if I make them go away, it may end up that this thing will start simplifying to that other side. So what do you need to get rid of? A cosine and a sine. Okay? Those are the 2 things you need to get rid of. So what I'm going to have you do is, we're going to do a parenthesis on that, and we're going to multiply this by sine theta cosine theta over 1, because we have to get rid of the cosine and we have to get rid of the sine. So we're going to do this like this, and this is a part of your proof. You want to show this step. Okay, like that. Okay, now what you want to do on this is, I find a lot of times in this class students don't have as much experience as I would like in working with complex fractions, so just kind of look at this in your head. You're doing a distributive property. So if you take sine cosine times sine, you're going to get sine squared theta times cosine theta. Do that in your head. Now, if you look at this part of the problem right here, what happens? Cosines cross out, so what are you left with? Sine squared theta. Okay, you can kind of process that in your head, okay. All right, now go to the bottom. Okay, if you go to the bottom on this, and I'm going to write some of this to the side because I don't want to mess my pretty proof up. But just to show you, if you don't see this, when you're taking this thing in red times this, what happens? Okay, so you're left with cosine squared theta. Okay, then you're multiplying this by this. I'll kind of draw a circle around that. So what cancels? Sine. So you're left with cosine theta like that. Okay, so that's the idea. Now, what we're going to do on this is, factoring is a big deal. Okay? Does the numerator factor? Is there a common factor? The numerator. Sine squared. Okay, you're going to take a sine squared out. So that you have a common factor of sine squared theta. Take it out. Sine squared times cosine squared will give you the first term. Sine squared times 1 will give that. So you have to know how to factor to do a lot of these proofs. Okay. How about the denominator? Now you can take a cosine out of that. Okay, so you want to take cosine out of that. Okay, what goes inside is cosine times cosine is going to give cosine squared theta. Cosine times 1 like that. Okay, what happens? Got to cancel. That goes away. Okay, we'll just keep working with it and see what we get. And this is probably a point in time where it's a good idea to look at what you're trying to prove. You're trying to prove a sine tangent. Okay, so right now we have left sine squared theta over cosine theta. I see a sine. Do you see a tangent embedded in that expression?
Yes.
Yes, you see a sine over cosine, right? So the best way to write this out is just write the step like this, right? Sine theta times sine theta over cosine theta, and you're done. Okay, so sine theta is left alone. This part right here is the tangent theta. So that's the proof. Okay? We started with the left side. We did everything correctly mathematically, and we ended up at the right side. Isn't that cool? Okay? It is. It's just this stuff I love doing this stuff. So if you're bored on a Friday night, just get your trig book out and just start proving stuff. Okay? It'll keep you out of trouble. Nobody ever got thrown in jail for doing proofs, I guess. Okay. I'm not saying that you guys would do anything bad, of course. All right. So this problem, it doesn't really matter which side you start with. I'm going to just kind of lead you through this last one here. So let's write down the right side, and we'll go through this. This is an example of a problem where you have to apply kind of a trick to. So I wanted to show you one example of this type. So what you end up having to do on this is you can multiply. The thing that ends up happening on a problem like this is you don't have any identities for just a cosine or a sine other than 1 over secant, 1 over cosecant. It's a lot better if you can have a sine squared because you have more options. So what I'm going to show you to do on this, I'm going to show you the trick, is you're going to multiply by the conjugate of the denominator. You can do this. You can multiply a fraction by anything you want to. So let's just do this. And this is something that, a mathematician just had to play with, and eventually they stumble on to this actually works and kind of helps in this problem. So when we do this, we're going to go ahead and leave the numerator factored. The reason we're going to leave it factored is maybe we're going to have some cancellation somewhere. Now, what do you do with the denominator on this? What does it look like? That's just foiling, okay? And you can write all steps out, or you can do it in your head if you want to. So if you do that, you would have 1 times 1 is 1. Okay, then you would have minus sine theta. You can bypass this if you can do this in your head. Plus sine theta minus sine squared theta like that. Okay? Now, the numerator, leave it alone. So you're going to have cosine theta times 1 plus sine theta. Okay, this cancels out. So you could bypass that previous step. At this level of a class, if you want to do that in your head, do it in your head. I don't care. Okay? Now, you got to think about factoring. Now, this is a good point to look at what you're trying to prove. Okay? It looks like what you're trying to prove is that this is going to be sine theta plus 1 over cosine. Now notice, I have a sine theta plus 1 there, don't I? Somehow I got to work with this cosine here. Well, what identity do you think is going to be helpful? This one. Yeah, exactly. So what we're going to do is, notice if you take this identity and move the sign there, you're going to get cosine squared theta equals 1 minus sine squared theta like that. Okay, so then what do we replace 1 minus sine squared theta with? Cosine. So now we have cosine theta 1 plus sine theta all over cosine squared theta. Now what happens? One of the cosines cancels out. Now you can do that in your head too. I don't care if you do that in your head. But I'm going to write this step, but you could bypass this step if you wanted to. So you could write cosine squared theta times itself like that. That crosses out, and you are done. Okay? Yeah, I'm just going to rewrite that as sine theta plus 1 over cosine theta, so that's it. Okay, that's a harder one. Okay, but that's something to pay attention to when you're doing a proof is think about stuff like cotangents and stuff like that. Now, I could just sit here and do these all day, literally, and never get tired of it. But one of the things I wanted to say to you is the only way to learn how to do this is just to get in there and work on it, of course. But I've tried to show you enough examples of different types of proofs to give you the idea, okay? And you'll have fun with them. You really will. You'll really see. I always say if you're studying math